today I'm going to do an introduction to sensors. And as I said, please drop questions in chat or speak up if I say something that doesn't make sense. The objective of this presentation and what I'm doing here is that I would like to make sure that students have an idea about different sensors that are available and commonly used in FRC. Several of these sensors have variations that I don't explicitly cover. And additionally, for a lot of sensors, it's going to be important to just learn how to read a data sheet or a user guide in general. A lot of sensors are not FRC specific, and so you got to read the same documentation that you would if you were a real engineer wanting to use that sensor. But don't worry, mentors are here to help you, and we can help you decipher a data sheet and all that type of stuff as well. But I wanted to at least give an introduction to some of these things here. Sensors are used to provide feedback, particularly to provide feedback about a mechanism or maybe about a game pieces. So some examples could be to be able to know the angle of an arm, knowing the velocity of a flywheel, if it's going at 3,000 RPM or 5,000 RPM. In addition to knowing the velocity of the flywheel, you need a sensor to be able to accurately control that speed as well. Sensors are, of course, used for calculating the distance a robot has traveled, particularly in autonomous mode. And it can be used to tell if a game piece is successfully being brought into a robot and being controlled within your mechanism. You'll need to know a little bit about the difference between digital and analog. Those are two different types of ways that data can be passed from a sensor to the robo-Rio or to a motor controller. Sensors will have an output that's either digital or analog, and then the robo-Rio and the motor controller have digital inputs and analog inputs. Sometimes you'll see those just referred to as DIO or AIO. Something that is maybe a little bit more advanced, but for our veteran students that are familiar, the analog sensors need to be in a 0 to 5 volt range, and there's different ways that we can make that happen. And those analog sensors are sampled at 12 bits. And basically what that means is that in the range of 0 to 5 volts, it can sort of sense as small of a change as 1.2 millivolts. In reality, it's not really that quite refined because you'll get noise. So those last couple of bits aren't that meaningful. And so you can't really get resolution all the way down to 1.2 millivolts, but that might be useful if you're looking at a sensor and trying to figure out if that's useful for us or not. Digital sensors, on the other hand, read one of two values, and you'll see that referred to as either high, low, true or false, or open and closed. Those are all common terms used for digital sensors. Another thing that I don't have covered in here is that on the robo-Rio, digital sensors have something called a pull-up resistor. So by default, they all read high. Limit switches are the most common type of sensors that you'll see used. I really think that pretty much every team should plan on having limit switches somewhere in their robot if you're doing anything more than just driving. Limit switches can be very useful for preventing a mechanism traveling past a point where it's safe to do so. So typically you have a hard stop as part of your mechanism where maybe an arm can't go past a certain point or an elevator can't rise higher than a certain point. And you don't want to drive your mechanism into those hard stops all the time. You'll damage your mechanism, you'll burn out a motor, things like that. So soft stops are a good way to do that. You can do soft stops either through other sensors or through limit switches. And basically whenever that switch gets hit, that tells you that you're at a point, you're getting close to your hard stop and you want to stop your mechanism and hold it at that position. So pretty much any elevator or arm will benefit from having some kind of a limit switch. And it's also safest to have the limit switch beside it. I don't know if you can tell with my mouse here, but you don't want the mechanism to slam into it this way where it's pushing the switch down this way. You actually want it to come across from the side. That way, if for some reason it does go past it, you're not destroying your limit switch. It would just go into the hard stop. So it comes by the side and then it's big enough that it just bumps the lever arm and pushes it into the switch rather than driving it into the button direction of the switch. Limit switches are really great because they can be plugged directly into the motor controller or the robo-Rio. If it's plugged directly into the motor controller will automatically stop applying power if the limit switch is activated. And the motor controller needs to know if it's normally open or normally closed, which I'll talk about in a second here. You can see an application of limit switches on the right here of our 2017 robot. We had these collars that had an edge flattened out, and they were about 90 degrees rotated from one another. So when the intake was down, a flat edge was in a position where the lever was no longer pushing down on that button. And then when the intake was up, it switched to the other limit switch. So we had two different limit switches here with two collars. And basically one of them was always depressed, and we were just looking for it to release when we got to either the down or up position. Because it's a common question whenever we start wiring up a limit switch, and it can be a little confusing if you haven't really spent much time thinking about it. This is a nice little cutaway of a limit switch. Hopefully everybody's able to see it okay. I'm gonna, whoops, maybe I can't zoom in. Let me see if I can zoom in just a little bit here. Zoom, nope, that was the wrong way. So there's this lever, which is connected to this push button. And when this push button gets pushed down, this contact goes from touching the metal that's up top to touching the metal that's at the bottom. And so what you'll see is that there's this pin, which is called the common, this one, which is called normally open, and you'll often see that abbreviated as NO. And then this pin, which is usually abbreviated as NC, which stands for normally closed. And so what that means is when the switch is not depressed, the contact is touching this. So that's why it's normally closed. And it is only open when the push button gets pushed down. And same thing for the normally open. It's normally not touching it until the switch gets pushed down, and then it gets closed. And so what you do is you have two of those connected. Let me zoom back to fit. And so you'd always have common connected to ground, and then you would connect your signal to either the normally open or normally closed, depending on how it is that you want it to work. And so you would only do two of the three contacts connected to the Robo Rio or to the limit switch input of a motor controller. And normally open means that the mechanism will continue working if the limit switch is broken or not plugged in or something like that, which hopefully makes sense if you think about it. It's normally open, so normally this contact isn't doing anything because there's normally a gap here. So if the limit switch is broken or if it's not plugged in, the Robo Rio or the motor controller wouldn't be able to tell any different. So if for some reason the limit switch is broken or not plugged in, the mechanism would basically still work as normal. Versus if you're plugged into the normally closed, well, now you know when the limit switch is plugged in or if it's broken. And so if you have it wired to normally closed and something happens to it, now the mechanism won't be able to close or operate at all because it will think that the switch has been depressed, and so it's only going to be able to go in the one direction. Now, of course, depending on what you have in programming, that may not be quite right. That you may be able to have either some limited functionality or something, just depending on how the programming is implemented. But normally, or in a usual situation, that's the difference between doing normally open or normally closed. If it's really important and you want to be able to work without the limit switch and you have the extra inputs available, you can actually wire the normally open to one digital input and the normally closed to a different digital input. And if both of them read the same value, then you know that there's a fault and the limit switch is either broken or not plugged in. And so they have to read different values in order to take any action based on it. So if we had a limit switch and we wanted to make sure that if it was broken, that we would still be able to work with some other method, that's how you could do it, is just using two different digital inputs. Any questions about the limit switches before I move on? Okay. The potentiometer is another sensor that we use frequently. It's relatively cheap. This one is an analog sensor. And so it doesn't really matter if you connect ground to 1 and voltage to 3 or vice versa. But the middle one, this 2 signal, would get connected to your signal input. And so when the potentiometer spins and it spins all the way to one side, it's connected to ground. And then you've got this track. And when it spins all the way around to the other side, you get all the way to voltage. So you get a value between 0 and 5 volts. Really, you get a value between ground and whatever voltage you have here. But the analog sensors for the Robo Rio should all use a 5-volt sensor. So as the potentiometer is rotated, you get a value between 0 and 5 volts. And the thing with potentiometers is they have a limited travel. So some potentiometers have less than one turn, maybe only like 250 degrees of turn. And then some of them have multiple turns. So it can be 1, 3, 5, or 10 different turns. So it can be up to 10 turns for a potentiometer. Generally speaking, you want to try to match the number of turns that you need for your mechanism to try to get the greatest resolution. Your programmers will thank you for that. And so it's useful for anything that has limited travel, especially like an arm. We used it on our 2018 robot for an arm. It can also be useful if you wanted to with an elevator. Sometimes it actually gets turned in, or you use it as something called a string potentiometer, or you can get a multi-turn if you've got some kind of thing that rotates less than 10 turns. You could use a potentiometer there. A good thing about potentiometer is it always reads a real value. So your wiper might be left in this position. If you get a power glitch or you turn off and back on, when you turn it back up, it's going to read the same voltage. And usually for robots, we use them as rotary potentiometers, but you can get linear ones instead, or slide potentiometers. And those might be useful for like a custom driver station. You can think of it as like a slide that goes between 0 and 100% or something like that. So I wanted to kind of walk through an example real quick of why you might want to match potentiometer turns. So a 10-turn pot, you'd have 360 degrees times 10 turns, so you'd get 3,600 degrees. And as I mentioned earlier, there's 12 bits of resolution. And what that ends up meaning is you get 0.88 degrees per bit. And like I said, the last couple of bits are really noise. So if you say that the last 3 bits are all noise, that means that you only have about 7 degrees of resolution. And on a 3-foot arm, 7 degrees at the end of it is going to be off by 4.5 inches. It's just going to make the programmer's life difficult if they're trying to control it with any kind of accuracy or repeatability. So generally speaking, you want to try to get that to be matched as reasonably as possible. Any questions about the potentiometers? Oh, I've got, I stole this from a slide that 2468 did. There's a bunch of different ways to mount it. Oh, okay, never mind. There's a bunch of different ways to mount potentiometers. You can have a bore in the shaft that the potentiometer can be put into. You can use a coupler, or you can also have a separate gear that the potentiometer goes into that doesn't actually do anything other than just connect to the potentiometer. So those are all common ways that you can connect to a potentiometer. Any questions so far? All right. Next up are encoders. And I think most people on the team probably hear about encoders a lot for our drivetrain. But there's a lot of different kinds of encoders. And it kind of breaks down mostly into relative, which sometimes you'll hear referred to as quadrature, rotary, or incremental, or absolute encoders. And so a relative encoder is really useful for anything that you're trying to just measure the change in angle. You don't need to know the absolute orientation or absolute position. Something that can be difficult with a relative encoder is that if you lose power, it resets to 0. And so it's best used in drivetrains and flywheels. However, it can also be used with additional sensors for arms and elevators. Another great thing is that relative encoders are included in all brushless motors now. And so that's a really great reason for using either a Neo 550, or a Falcon motor, is that it gives you an encoder directly at the motor. But sometimes you still want a relative encoder at closer to the mechanism. And then there's absolute encoders, which are similar to potentiometers, but they have unlimited turns. They are a lot more expensive than potentiometers, but they're useful for arms or steering, like in Swerve. And they can be analog or digital. Digital requires more connections, but you can use either. And so there's a bunch of different types of absolute encoders out there. And actually, a common one used is the CTRE mag encoder. And so the mag encoder is both, it can be either a relative or an absolute encoder. And you can actually even use it as both if you want to. So here's some different pictures of encoders as examples. So the one on the far left here shows the mag encoder and the thrifty swerve. So there's a magnet here, and then the mag encoder would be in this housing here, and it basically senses the rotation of the magnet. And so that's how it uses that. So there's no actual contact between the encoder and the magnet. And it does mean that you have to have a bore in the shaft that the magnet can stay in securely. There's also through bore encoders. So a new one that I'm excited about is the hex through bore encoder. Really useful for things that are maybe a little bit slower RPM. And then a way that I don't think Kara ever felt great with, but we have used a couple of times, is actually just using surgical tubing and zip tie to connect an output shaft and put surgical tubing around an output shaft, zip tie it there, and then put the other end of the surgical tubing around the potentiometer, or I'm sorry, the encoder shaft, and zip tie it. And it's probably not nearly as precise as other methods, but for the way that we were using it, it worked out okay. Any questions about encoders? Okay. A gyroscope is another one that you might be familiar with if you've talked to the programming team about autonomous stuff. So it measures angular velocity, and so it's a rate of rotation in degrees per second. It provides heading, which sometimes you'll see referred to as yaw, and basically all that is the direction that the robot is facing. And it does that when it integrates the data. And so for those of you that have taken calculus or pre-calc, I forget when Raman sums are first introduced, but it's basically doing a Raman sum. And so it's sampling it, and then it's accumulating that data. And so you'll get what's known as drift, because that accumulation is not perfect. It all depends on your sampling rate and all that kind of stuff. And so over time, your gyroscope tends to drift, and you have to do things to compensate for that. There's other reasons that a gyroscope can drift as well. But a gyroscope is commonly packaged inside of an IMU module along with other sensors. And so we don't typically have something that is just a gyroscope sensor on FRC robots so much anymore. I know back when I was doing it, we had a separate gyro that we would use because we were trying to tell, go or like maintain a heading to go straight, turn 45 degrees, things like that. Also, I see commonly that people think that a gyro can't be at the center of a robot, or it has to be at a center of a robot. It can't be off center. But that's not really true. And this is a meme that a friend made a while ago that I think is always funny and accurate. There are reasons to have an IMU at the center of a robot, but for the gyro, it doesn't really matter so much. The gyro can be off center. There's also accelerometers. And so accelerometers are pretty straightforward. It measures accelerations, which is the change in rate of velocity, so meters per second squared. It can also be used to measure tilt by comparing its output with gravity. So if we have an accelerometer on the robot, we should always be able to sense gravity, and then comparing what we are getting from our accelerometer data and what angle we have to gravity, we can tell if the robot is tilted one way or another. So since it is always measuring gravity, it's best to mount the sensor so that gravity is only measured in a single axis. So you don't want an accelerometer mounted at an angle or anything like that. You'd like it to be flat in some orientation. Typically flat relative to the ground is preferred for most IMUs. They have a Z up orientation. And it's also commonly packaged inside of an IMU. So again, you don't typically have a standalone accelerometer sensor on the robot. There is a 3-axis accelerometer built into the RoboRio, which is convenient. An example for how you might use this is that we could, in theory, use this to auto balance on the shield generator at the end of the game for this year. So when we climb, we could look at our accelerometer data in the RoboRio and tell if we have gravity going directly down on our robot, or if we need to do something to drive one way or another to try to level it out. So that's not something we ever had time to do. But that is something that we definitely could look at doing. And then moving on to inertial measurement units, or IMUs. This combines gyroscopes and accelerometers, I'm sorry, and sometimes it adds magnetometers and barometers into a single package. And so IMUs now are becoming very common. It's especially useful for autonomous path following and stabilization. So it provides accurate orientation or heading or yaw, whatever you want to call it, your angular rate and specific force measurements. Some commonly used IMUs in FRC are the Pigeon IMU, the NavX2 IMU, and analog devices IMU, ADI. The ADI IMU drifts less during a match. So if you're trying to do something throughout a match, the ADI IMU is really great. However, the Pigeon and the NavX2 have a lot of software documentation and examples, so it's easier to use. All of them are getting pretty small. The NavX2 is probably still one of the larger ones. It takes up a good chunk of space on the RoboRio here. You can see the analog devices one here just takes up a little bit of room at the top of the RoboRio. And then the Pigeon IMU, it can be used either on the CAN bus or it can be connected to the data port of a Talon SRX to get the IMU data from that. So all of those are different ways that you can get IMU data especially for programming autonomous modes. Any questions about IMUs? Okay. So this is just a long thing that I've included in here. I'll put this in our meeting recaps channel if anybody wants to be able to go and read this later. But this just talks a little bit about how with IMU mounting, it can be useful to have the IMU mounted as close to the center of rotation as possible. Not necessarily the center of the robot, but the center of rotation. It's depending on what you're doing, it's not necessary. If you're only using the gyro aspect of it, then it doesn't matter. If you're using the accelerometer aspects of it to add in and refine your data, then it does matter a little bit more. Distance sensors are another thing that are used in different applications for FRC. So they're often going to be ultrasonic or infrared. And there's a type called time of flight, or you'll see it called TOF. And basically what that does is it bounces the infrared or ultrasonic sensor signal off of an element and uses the time to calculate how far away that is. They work only for a certain range. And so I've got an example. This one from playing with Fusion is a time of flight one. You can also do where it's like a one-sided beam break, which I talk about beam breaks on a later slide. I thought I had it before it. Where it won't tell you the exact distance that something is, but it will tell you if something is within that distance. So, it's just sending out a pulse, and if it doesn't get anything back, then it says, okay, there's nothing here. Versus if it sends out a signal and it bounces back, then it says, okay, there's something within this range. Beam breaks are similar to the distance sensors, but it doesn't tell you like a distance. It just tells you there's a IR beam that goes between two different parts of the sensor. And if anything breaks that IR beam, you get a notification, you get a signal somehow telling you that the beam is broken. So that's very useful for telling if a game piece is in a certain location. You could have one on either side of an intake, for instance, if you're just picking up like a power cube in 2018. You could have a beam break on either side of your intake, and when a cube comes in, that beam will be broken, and you'll know that you have a game cube. We could do a similar thing with our ball tower. We could have beam breaks that go up and know roughly how many spots or balls are in there. We were attempting to use a distance sensor for that this year. We just didn't get far enough along to do it. One thing that I have seen some teams complain about is the potential for IR oversaturation at competition. But I don't know how real of a concern that is. It may depend on where it is that you've got it. A sensor that we haven't used much yet, which I think might be useful to start looking at more, is a reed switch. And I just took this pretty much from a web page that really covered it, I think, very well. You can kind of see in this diagram here, there's two flexible, thin reeds made of ferromagnetic material. And so when a magnet gets close enough, it actually pulls those contacts together and says that now it closes it, just like a limit switch. You can also do it. This is like a normal limit switch where one of these is a normally open and one of them is a normally closed. Or you can just do it with a 2. You don't need to have 3 pins on it. And I've got some, man, I thought I had my Hall effect one here first too. So I'll talk about Hall effect sensors in a second, but a nice thing about reed switches is that you don't need to do anything other than use the magnetic field to bring about the switching action. So it's very passive in that way. It's also not sensitive to the polarity of the magnet, like a Hall effect sensor is. So a Hall effect sensor is very similar, except instead of just being 2 flexible reeds, it's actually what's called a semiconductor transducer. That's not a word that I expect you to understand. It's just to kind of describe that it is a little bit different. And it generates an electrical voltage when a magnetic field is present. So that basically means when a magnet gets close, it's not that things are physically closing or anything like that. It just senses the magnetic field and will switch either high or low. The polarity and the direction do matter and are crucial to the proper function of a Hall effect switch. They have no moving parts, so they are unaffected by mechanical shock. A reed switch could break from mechanical shock. You imagine that, we go back to this thing, and these are thin, flexible reeds, so it's possible that if you hit it real hard that they break, and now that reed switch won't work anymore. So since it doesn't have any moving parts, Hall effect sensors are much more, I can't think of the word, reliable, I guess. They won't experience wear and tear, even if they're switching at a very high rate. I thought that these videos were really great. They're both very short. Hopefully I'm sharing for optimizing video. If I'm not, please let me know. But you can see this is a reed switch. It looks like a resistor up here. And then he's just trying different magnets to show that the bigger the magnet, the further away it can be. And you can also see that he's having the magnets, what I would call, I guess, sideways in this example. And so when he has it sideways, and that's a big magnet, so it can be really far away, and the switch closes. So that is a reed switch. And now I'll show the Hall effect sensor. And so you can see now actually that the magnet is oriented in a different way. It's tough to tell with a tiny magnet. But it's the same type of thing. You get a magnet close enough and it closes. So I think reed switches and Hall effect sensors might be useful when a limit switch might not be able to work in a given application. All right, so to summarize, sensors in conjunction with software are used to allow you to use mechanisms to their fullest capability, such as controlling velocity of a flywheel, controlling an arm or an elevator to a repeatable, precise location. It's good for a safety mechanism to make sure that mechanisms don't go to a hard stop or beyond. And just knowing information about a mechanism. So maybe knowing its position, knowing if it has a game piece or not. And sensors are one of the areas in FRC where it's very valuable to not just rely on FRC vendors. There are some sensors that benefit from FRC specific applications. You'll see that the IMUs that I referenced are all built pretty much specifically for FRC. However, there's a lot of a lot of sensors that are widely used outside of FRC and outside of FIRST. So there's little need for FRC vendors to sell them or specialize them or anything like that. So if you're looking for switches or encoders or potentiometers, more than likely it's best to look at like DigiKey or Mouser or other vendors that are not FRC specific vendors. So I'm going to stop sharing it. Well, I don't know. I do have, this is a string potentiometer. So it uses a potentiometer, typically a 10 turn, and it has a string wrapped around the potentiometer shaft more or less. And there's a spring that helps retract the spring. A spring that retracts the string. And so this is showing kind of a simple string potentiometer. So you can see he's basically got one of those clips, string clips that like you can have a badge connected to your belt or something like that. It gets wrapped around this potentiometer. And then when you pull the string, it comes out, it turns the potentiometer shaft. And then the spring, the badge clip here pulls the string back in when it doesn't have any force. So that can be very useful if you can imagine that his finger is a point on an elevator. That could be useful for elevators. However, also, if you can imagine, strings can break relatively easily in FRC. So if it's not well protected or guided, it can be a weak point in your design. So something to keep in mind, especially from a programming aspect. So it's not used as often